Looking back at the edge of a black hole, you'll see 100 versions of yourself. This isn't magic. It's the photon sphere. 15 seconds later, even light can't escape your eyes. Today, let's talk about a hardcore topic. What would happen if we threw you into a black hole? This time, it's not science fiction. It's really based on hardcore physics predictions. Before we throw you in, let's quickly review what a black hole is. Even Einstein, that old man, described a black hole as where God divided by zero. He didn't even believe such a thing could exist in our universe. But guess what? Humans actually found it. When those massive superdense stars reach the end of their lives, they undergo a grand transformation, collapsing into nothing. What they create is called a singularity, a mysterious point in spacetime, said to have infinite density, and thus infinite gravity. General relativity gave us a revolutionary idea. Gravity isn't a force acting on objects. It's just the result of spacetime bending due to an object's mass. It perfectly explains how Earth orbits the Sun, and how planets spin like they're circling their home. There's no solid black surface inside a black hole. The singularity hidden inside is just too dense, warping spacetime drastically, forming a deep well with vertical walls. In 1939, Einstein himself published a paper saying stars collapsing into singularities wasn't plausible and wouldn't happen in our universe. But coincidentally, in the same year, Oppenheimer, yes, that famous Oppenheimer, along with physicist Hartland Snyder, published a paper predicting that stars could indeed collapse into black holes under their own gravity. Now, let's talk about what happens if we throw you into a black hole. The most fascinating thing about a black hole is that anything can become one. Whether you're a star, a planet, or a tiny human like us, as long as you're compressed within the Schwarzschild radius, you can become a black hole. German physicist Karl Schwarzschild was the first to find an exact solution to Einstein's field equations. This discovery is both simple and beautiful. Take our Sun, for example. If all its mass were compressed into a sphere with a radius of just 3 kilometers, boom, it becomes a black hole. What about Earth? It would become a sphere with a radius of about 9 millimeters, roughly the size of a marble. If a human wanted to become a black hole, it'd be brutal. You'd have to be compressed to something unimaginably smaller than a proton. But if you could get that small, you'd become a black hole too. So, which black hole should we throw you into? I think it's time to toss you into one. But which one should we pick? We could choose a small one. But that's no fun. Let's go with a big one. Some black holes have event horizons larger than our entire solar system. That's billions of solar masses. But that's a bit too extreme. How about one closer to home? Sagittarius A*, the supermassive black hole at the center of our Milky Way. You're already orbiting it. It's one of the only 2 black holes humans have ever photographed. Now, let's set the scene. You and I fly there, parking our spaceship a trillion meters from the event horizon. We're sending you to the black hole. As you freefall, I'll stay on the ship to observe. Here's the key. General relativity tells us that time near a black hole can feel completely different for different observers, because the black hole warps spacetime so intensely. Interstellar showed this effect perfectly. To keep track of time, we'll give you a special watch. It shows how much time has passed from your perspective and mine on the spaceship. We sync the watch, and you're ready to start your black hole journey. As your journey begins, you'll see the black hole rapidly devouring matter. The scene is breathtaking. Matter gets heated to extreme temperatures due to friction. Simulating this on a regular laptop would take over a decade. In reality, that disk would be bright blue or even white. But in this simulation, it's made orange. For easier observation, you check your watch. It's only been 30 minutes. You've only covered 0.1% of the distance to the event horizon. So far, I'm only 11 seconds ahead of you on the spaceship. The time difference isn't too wild yet. Now we're getting closer to the black hole. The bending of spacetime around it is creating all sorts of weird visual effects. Light from the sides or even behind the black hole gets bent before reaching your eyes. Let's check the time again. You've been gone for 2 hours, covering 1.4% of the distance. Now I'm 44 seconds ahead of you on the spaceship. This time difference is getting a bit concerning, but it's still not too crazy. The dark region in the black hole's shadow seems to grow faster than expected. That's due to gravitational lensing, bending light that would have passed by you onto your retina. A long time passes, and you finally check your watch again. This time it shocks us. From your perspective, it's been about 12 hours since you left. But for me, on the spaceship, I've been watching you drift toward the black hole for nearly 15.5 hours. We're really close to the black hole now. Things are about to get very weird. Before you reach the singularity, you'll arrive at a strange and magical place. If you were frozen in time at this special spot and looked around, the sight would absolutely blow your mind. You've reached the photon sphere, one of the strangest places in our known universe. In the photon sphere region, gravity is perfectly balanced, allowing photons to orbit the black hole. It's not matter emitting or reflecting light. The photons themselves are trapped in orbit. If that light moves tangentially to the black hole, it can stay in orbit. But if the path shifts even slightly, the photon either falls into the black hole or escapes into space. Under these specific conditions, if you were frozen at the photon sphere and looked around, you'd see a mirror image of yourself facing away. You'd see multiple copies of the back of your head staring into space. You're literally looking at yourself, as if standing right beside you. No fancy tech needed. It's all due to the warping of spacetime itself. As you continue your journey, you're getting very close to the event horizon. Now we've passed the photon sphere, and the black hole takes up more and more of your view. It feels like you're being swallowed by darkness. That's because the darkness warps around you, showing the back and sides of the black hole's shadow, along with parts that would normally be visible in flat spacetime. You've been gone for 13 hours. In 24 minutes, you'll cross the event horizon. But from the spaceship, I've been watching your journey for nearly 20 hours. Another 18 minutes pass, and you check your watch again. Now I've been observing you for nearly 40 hours. Your final 18 minutes felt like 18 hours for me. The final moment arrives. In just 6 more minutes, you'll cross the black hole's event horizon. You close your eyes, take a deep breath, and check your watch. It seems broken. It shows I've been watching you fall for an infinite amount of time. But it's not broken. Physics is just that wild. I've spent decades on the spaceship watching you slowly approach the event horizon. Eventually, I see you turn red, meaning I'd need an infrared telescope to see you. I'll never see you cross the event horizon, even if I could live forever. For you, those final 6 minutes feel like eternity to me on the spaceship. It sounds like science fiction, like a daydream, but it's absolutely real. It comes straight out of Einstein's equations. Now you're inside the event horizon. So what happens inside a black hole? Strangely, it's hard to notice when you've crossed the event horizon. You can still look out at the universe, seeing distant stars, even our spaceship floating in space. But all that light, like you, is headed toward the singularity. You've passed the point of no return, that point of infinite density. All our physical laws break down. Time itself stops. To escape the singularity's gravity, you'd need to move faster than light, which we all know is impossible. There's a common misconception. If you look out at the universe, extreme time dilation would let you see the entire future of the universe, history unfolding before your eyes. But that's not true at all. Because of aberration, as you approach the singularity, you'd see the external universe compressed into a tiny ring. Finally, when you're close enough to the singularity, Your feet would be stretched ahead. Your body elongated in a process called spaghettification. You become one with the black hole, drifting together in the universe. Until eternity. The whole process is chilling to think about. Yet you can't help but want to explore it. Black holes, these mysterious celestial objects, are both terrifying and fascinating.